Good morning to everyone. Today we are going to discuss about the topic on instruction level parallelism. So this is the basic topic in computer architecture as well as in the high performance computing subject. So what is instruction level parallelism? So before going to that, myself Arpunita Gauri, I am working as an assistant professor in Erode Singundar Engineering College at CSE Department, Tirupati. Okay. So what is ILP? What is instruction level parallelism? So this is one of the technique to improve our computer performance. So what is parallelism means we are going to do multiple tasks at a time. So the processor going to execute multiple instructions at a time so that we can reduce the execution time as well as we can improve the performance of a computer. Okay. So in parallelism we are having two different kind of parallelism. One is data level parallelism and task level parallelism. Okay, one among that, the instruction level parallelism is the main concept in data level parallelism. So these are all the overall view we are going to discuss about in ILP. But today we are going to discuss only about the concepts and challenges. Okay. After that we are going to discuss about the several techniques to overcome what are the challenges we have faced in ILP. Okay. The technique one was dynamic scheduling, and another one technique is dynamic hardware prediction. And one more thing is multiple issue statements. We are going to issue multiple instructions at a time so that how the processor can handle the instruction and execute the instruction. We are going to discuss all about that. And the next one is what is compiler support. So compiler also can help in exploiting ILP. Okay, so what is the role of compiler in this? And next one is hardware support for extracting more parallelism. So what are the hardware changes we have to made in the post processor so that we can execute more instructions at a time, so we can improve the parallelism. And the next one is studies of ILP. In that we are going to discuss about limitations of ILP. So in order to improve ILP, what are the limits we are having? Okay, so these are all this is the overview of the instruction level parallelism chapter. So today we are going to discuss about only concepts and challenges in ILP. Okay. Uh, so this is one of the these are all the techniques which are used to improve ILP, and these are all some hazards and stalls and dependencies which were arised during the ILP. Okay, so during ILP we will get more hazards and more hazards and stalls. So in order to reduce these stalls and hazards, we have to use some specific techniques. Okay, this will be discussed later. Okay. So next, what is ILP? So ILP is a principle that there are many instructions in code that don't depend on each other. That means it's possible to execute those instructions in parallel. So we have to pick up a set of instructions and we have to execute those instructions in a parallel way, which means that the set of instructions should not be dependent on each other. Okay, if there is any dependency among the instructions, means we cannot execute those instructions in a parallel way. So in that situation, the dependency will arise, the stall will arise, the hazards will arise. So we have to choose the set of instructions that should not be dependent on each other. Okay, if the instructions are independent, means they can execute in a parallel way, so that we can make the in ILP to achieve. Okay, so next one, in order to do the ILP, we have to make sure that the compilers to analyze the code, and we have to make sure that the hardware to be even smarter than that the code, which means that first the compiler should analyze what are all the dependent codes, what are the dependent instructions, what are all the independent instructions, like that. And we also the hardware should support the multiple instructions to execute at a time. Okay, so we need more hardware setup to execute multiple instructions at a time. So these two are the basic requirement for doing the ILP. So next one, instruction level parallelism. So in this first we have to find the basic block, and we have to discuss about the loop level parallelism and what is loop unrolling. Okay. So first one, the set of instructions between entry points and between branches. A basic block has only one entry and one exit. Typically this is about 6 instructions long. Okay, so the basic block is a set of instructions that should have one entry point and one exit point, which means that it says that the basic block will be any conditional statement or any looping statement, like that. Okay, so the basic block should have only one entry point and only one exit point, about 6 instructions, or we can have many instructions also in the basic block. Okay, so what is loop level parallelism means? The parallelism that exists within the loop. Such parallelism can cross loop iterations. So for example, if we are having a for loop, means we are going to execute the instructions which is inside the for loop. We are going to execute multiple times the same instructions, right? So that is what loop level parallelism. So that multiple times we are going to execute the same instructions means we can execute that in a parallel way. So if we can achieve that, means we will call it as a loop level parallelism. So in order to achieve the loop level parallelism, we are going to use one technique called loop unrolling. Okay, so what is loop unrolling means? We will see the example so that you can understand easily. Okay, so loop unrolling can be done either by the compiler or by the hardware, and both the compiler and the hardware is able to exploit the parallelism inherent in the loop, which means that we have to unroll the loop. So next we will see an example so that we can understand. So this is the for loop. For I equal to 1, I less than or equal to 1000, I plus plus, which means and x of I equal to x of I plus s. So this is the basic for loop. This loop will execute for 1000 times, right? For I equal to 1 to I equal to 1000, which means that this statement is going to execute 1000 times. So this is the simple looping statement. So the equivalent MIPS code, that means this is the assembler code for the for loop is, first we have to load the value, right? So first we have to load the value R1 to F0. Okay, so this is O of R1, which means this address of R1 to F0. Next we are going to add F0 and F2. So F2 is a scalar value, so this S value, right? So this S value from F2. So we have to add that F2 and F0, and we have to store the result back to the F4. Okay, so next F4. So we have to store the F4 back to the register R1 so that this loop will be continued. Okay, again we are going to store back the F4 into the register R1. Okay, so next subtract R1 comma R1 comma 8, so which means that this is the decrement pointer. Okay, so next this is the branch not equal to statement. R1 is loop, which means that R1 not equal to 0. So we have to execute this code till R1 gets 0, not equal to 0. Okay, so no operation. This is NOP, means no operation. So this is for in order to reduce the branching delay. Okay, so this is the delayed branch slot. One clock cycle will be simply leave the one clock cycle. This is no operation. Just we are going to give some delay to this branching statement. Okay, so this is the equivalent MIPS code or assembler code for the given for loop. Okay, so next technique is how we are going to do loop unrolling in this. So look at this. We are having some dependencies over there, right? First we have to find the dependencies or hazards in this, so that we can do the if there is no dependencies means we can execute that code in a parallel way, but if there is some dependency means we have to do some technique to overcome that dependencies. Okay, so look at this table. So instructions producing the result, instructions using the result. Okay, so this means that this should be the first instruction and this should be the second instruction. And if what is the delays in the, what is the latency in the clock cycles? So this table depicts that. Okay, so the first instruction may be an any ALU operation. ALU operation means any arithmetic and logical operation. FP in the sense floating point. So the first instruction may be floating point ALU operation, and the next instruction should be another FP ALU operation, means the delay should be 3 clock cycles, which means that this first instruction cannot be executed in one clock cycle. It will take 3 clock cycles. Okay, the next one, the first instruction may be an FP. The first instructions may be an FP ALU operation, and the next instruction is some store operation, storing double value, means it will take 2 clock cycles to complete the execution. And then third one, first instruction may be any load operation and the next instruction may be any FPALU operation, floating point arithmetic and logical operation, means this instructions can be these two instructions can be completed in one clock cycle as usual. Next load and the next double, means there is no delay, extra delay, there is no latency in this. And next one, first integer operation, next also integer operation, means there is no delay in the clock cycles. Okay, there is no need of extra clock cycles to complete the instructions. Okay. So first one, we are going to discuss this code. We are going to see what are the dependencies among the code. So look at here. This one is the load instruction and another one is the add instructions. Add instruction is a kind of ALU operation. Okay, so these two instructions comes under the situation called first load and then ALU. So this one comes among the third instruction, right? So first load and next FPALU operation, which means that the latency will be one more clock cycles. This cannot be executed in a single clock cycle. This needs two clock cycles to complete, right? Plus one. And look at that. F0, and also this F0 will be used in further next upcoming instruction, which means that there is a dependency among the instruction. And look at this, this is the F4, and here also we are using the register called F4. So this is also a one kind of dependency, right? So this is one add and one store. One add and one store. So this is same as ALU operation and storing operation. So this is same as this situation. One ALU operation followed by one store operation. So this will take two more clock cycles to complete the instruction execution. Okay. Look at the slide. So this is the number of clock cycles. So first we are going to load R1 to F0. Then because of the extra latency, we need one more clock cycles to complete the execution. So in second clock cycles we cannot execute any instructions. So it is a stall. Okay, ideal time. Okay. Next we are having the addition operation. So in addition followed by store means we need two more clock cycles as given here. Okay, so that two clock cycles, and the next one store and subtraction. So store and subtraction no need any extra operation, so just it is executed in parallel way. And the next from subtraction to branch not equal to a operation, this is the conditional operation. Okay, some need some stars. So this is the kind of two ALU operations, right? So there is a stall, and the next one also stall because of delayed branching. So this cannot be executed in one clock cycle. So this is the another one stall. So totally we need 10 clock cycles to execute this 5 instructions. So now we are going to use the technique called loop unrolling and out of order execution. So both this technique will exploit parallelism by changing the order of instructions and doing the loop unrolling technique. Okay, let us see in next one. So first we are going to do some out of order execution, which means we are going to change the uh, order of execution, order of instructions given. Okay, so before that, this subtraction, look at the example. So in before example, this subtraction instruction will be given after the addition operation, right? So this one. So in order to move from fourth instruction to the second instruction, we can avoid one kind of stall, and also two more further stalls also. In this two clock cycles, this subtraction instruction will be executed, right? So we can reduce this whole instructions in we can execute all the instructions in 6 clock cycles. Okay, only one stall. In previous example we get 5 stalls, and the number of clock cycles need to execute the instruction set is 10. Now we can complete this in execution in 6 clock cycles by changing the instruction order. Okay, so this is what out of order execution. So the program given in the order, we will execute the instructions in given order, means it is called in order execution. And if we are going to execute the instructions in by changing the order of instruction, means that is called as out of order execution. So this is out of order execution. Now we are going to do a loop unrolling technique. So loop unrolling technique means we are going to look at the example. So we are going to do this load, add and store operation in repeated way. That is what parallel looping instructions, right? We are going to do the same load, add, store, load, add, store, load, add, store, like that. Okay, so here I am having two loops, right? I have unrolled the looping statement, load, add, store, load, add, store, load, add, store, like that. Okay, if the and so here also we are having load, add, store, and then load, add, store. Next finally subtraction and branch not equal to. So I have unrolled the loop 4 times, 1 2 3 4 times. Okay, so this is loop unrolling. Okay, just I have unrolled the looping statement. Okay, look at here, there is a change in the code in loading instruction. In load instruction, first I have to load R1 value to F0. Okay, and then F0 plus F2 and store the result in F4, and F4 store back the result F4 to R1, and minus 8. Why I mentioned minus 8 means this R1 will be minus 8 for 8 bit, 1 byte. Okay, and store the value in F6. I have renamed the register in order to avoid a dependency. Okay, so in previous example the same F0 will be used here also. Okay, in order to do the loop unrolling, I have to change the register name so that I can avoid many dependencies. among the instructions. Okay, so that I have changed the instruction. This F2 value will not be changed. This F2 name will not be changed. Look at here, all the instructions. This F2 is same because the S value is same. Only we are going to change the value of x of I. If you have noticed in the for loop. Okay, so this F2 is same for all instructions, but we have to change the name of this R1 register value to F0. Here I have stored the R1 to F6 and F10 and F14. Okay, and I am going to store the result first looping statement. I am going to store the result in F4, and in second addition instruction I am going to store the result in F8, and third one F12, and fourth one F16. Okay, finally I am going to do the subtraction has 32. Why I have mentioned 32 here means because of I have unrolled 4 times. 4 into 8, 32. Okay, so 32. That's why here I have mentioned 32, and we have to do the branch not equal to comparison and start and no operation. So if I have unrolled the loop means the total number of clock cycles to execute this is 28. Okay. So still we can do this in better way because we have more number of stalls, right? Look at this. So we have done the loop unrolling, and also we are doing some changes in the code in the order of execution so that we can minimize all the stalls. Okay, so first we are going to execute all the load operation and all the add operation and all the store operation and subtraction and branch equal not equal to statement and store operation finally. Okay, so in this way, in previous way we get 7 clock cycles to execute per iteration, but here we get only 3.5. Okay, without any stalls. That is the major thing. Without any stalls we can execute all the instructions. Okay, what assumption we have made means subtraction is even though changes register. Before storing the instruction in subtraction we can do the changes in the register. Okay, so these are all the assumptions we have made. So in order to achieve the loop level parallelism, we have done two kind of technique. First one is the out of order execution, and the second one is the loop unrolling. So in loop unrolling also we get some stalls over there, so that we have made the changes in the code so that we can avoid stalls. Okay. So this is the summary of loop unrolling. So determine that it was illegal to move the store after the subtraction and branch not equal to statement, and find the amount to adjust the store offset. So first we have to find the store offset value, that -8, -16, -24, -32. So store offset value. Okay, and next second one, so determine the unrolling the loop would be useful by finding that the loop iterations were independent except for the loop maintenance code. So except that code x of I equal to x of I plus s. So the another looping statement will be independent of each other. Okay, we have to determine, we have to make sure that also. And we have to use different registers. In last example we have done F4, F8, F12, F16 like that. So we have to use different register names to avoid unnecessary conditions, unnecessary dependencies, to eliminate unnecessary dependencies. And we have to eliminate extra tests and branch and adjust the loop maintenance code. And next one, determine that the loads and stores in the unrolled loop can be interchanged by observing that the loads and stores from different iterations are independent. Okay, so in each iteration the load and store should be independent of each other. And we can schedule means we can rearrange the code preserving any dependencies needed to yield the same result as the original code. So in order to do the scheduling, what are the compiler perspectives to be supported by the compiler? Okay, so first we have to look for any data dependency. So what is data dependency means? So RAW if a hazard of for hardware. Hardware means HW means hardware. RAW means read after write hazard. So read after write hazard. So this dependency will arise if instruction I produces the result which is used by the instruction J. So first instruction I produces some result that should be used by the upcoming next instruction. Okay, if we are having such instructions set means there is a chance for data dependency. Okay, or else instruction J is data dependent on instruction K and instruction K is data dependent on instruction I. This is the cycle B. Okay. So this is the kind of data dependency. We have to find any data dependency over there in the instruction set. So next we are having another kind of dependency called name dependency. So in name dependency we are having two different kinds. First one is the anti-dependency and next one is the output dependency. So what is anti-dependency means? This is the kind of write after read hazard. Okay, so write after read hazard means instruction J writes a register or memory location that instruction reads from and instruction I is executed first. So first we are having instruction I. In the next instruction J write some memory location register value or some memory location that should be read by instruction I. That is called write after read hazard. The next one is output dependency, which means that both the instruction I and J going to write in the same register or same memory location. Okay, so this is called write after write hazard or output dependency. So these are all the kind of dependencies: name dependency and data dependency. So we have to avoid such dependencies over there. Okay. So this is also the same code, sample code. So look at here. So after unrolling the loop, we are having such dependencies. The red color intimated is name dependency. The blue color line is depicts the data dependency over there. So look at this. For example, load, add, store. This is one set of instruction, right? This load, add, store instructions. This F0 is used here, right? Instruction J. Instruction I writes the result and instruction J reads the same value. So this is called a data dependency. Okay, so look at here F4 and F4, both the instructions writing into the same way. This is called a write after write hazard. Okay, so look at this name dependency in the next loop. So here also F0, here also F0, here also F4, here also F4. So these are all the dependencies over there. So what we are going to do means we are going to make some changes in the instructions. That is, we are going to execute it in an out of order way so that we can avoid the dependencies, and also we can use the register renaming technique. We are going to renaming the register value so that we can avoid the data dependencies and name dependencies over there. And we are also having the dependency called control dependency. An instruction that is control dependent on a branch cannot be moved before the branch so that its execution is no longer controlled by the branch. Okay, so the instructions within the branching instructions cannot be moved out of the instruction. So we are having control dependencies over there. And also an instruction that is not control dependent on a branch cannot be moved to after the branch so that its execution is controlled by the branch. Okay, so an instructions within the branching statement we cannot move back to the code. Okay, So if we do means we cannot, we will arise some control dependencies over there. So look at here. So what are all the control dependencies over there? So this is the technique which is used to, what are data dependencies. So A, B and C. We have to evaluate uh, when to do some loop unrolling. Okay. So statement 2 uses the value a of I plus 1, which is computed by statement 1 in the same iteration. So a of I plus 1 is computed in statement 1, which is used by the upcoming instruction S2. Okay. S1 uses the value computed by S1 in the earlier iteration, since iteration I computes a of I plus 1, which is read in instruction iteration I plus 1. The same is true for S2 for B of I and B of I plus 1. So B of I, A of I, A of I plus 1, we are going to storing the value in A of I plus 1. In the next loop, this A of I plus 1 is used by the statement S1, and B of I plus 1 is used by the statement S2. So this type of execution is called loop carried dependencies. So the dependencies is carried over the looping statements. Okay. So this is one main thing. Loop carried dependency between iterations in the for loop. Okay. So this implies that the instructions are dependent and cannot be executed in parallel. Okay. So the loop carried dependencies cannot be executed in parallel way. Okay, so that's all about the instructions level parallelism. So what are all the changes, what are all the challenges we are facing during the instruction level parallelism. So next we are going to discuss about the techniques which are used to avoid the hazards and dependencies, and we can improve the parallelism. Okay, so these are all the techniques we are going to see in upcoming videos. Okay, thank you.